Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your channel Chandan Physics. In this video, we are going to discuss polarization vector, susceptibility, dielectric constant and relation between susceptibility and dielectric constant. Let's begin. Polarization vector P. In the previous video lecture, we discussed about the phenomenon of polarization. Means when a dielectric slab is placed in an electric field and the strength of electric field will decrease, and the phenomenon of appearance of charges on opposite faces of a dielectric slab induced by the external electric field, which is known as polarization. To define that polarization, a term is introduced which is known as polarization vector P. So, the induced dipole moment per unit volume of the dielectric is called polarization vector P. Let me say, let the induced dipole moment of the dielectric is equal to Pi. Induced dipole moment, since inside that of dielectric, electric field is produced as one end negative charge, another end positive charges are induced, so that creates induced dipole moment. And the volume of dielectric, let V. According to the definition of polarization vector P, then polarization vector P is equal to, that is, dipole moment per unit volume, dipole moment Pi per volume V, or P is equal to dipole moment. Let here we say d be the thickness of that dielectric slab. So, the induced dipole moment Pi is the product of charge into length of that dipole. So, charge Qi, length of that of dipole d, Q subscript I, ith charge V, Q I d. D the thickness of that of dielectric, and the direction of that induced dipole moment from negative charge to positive charge, its direction is from negative Qi to positive Qi, direction of induced dipole moment. And the magnitude of that polarization vector P is equal to Q I D divided by V, or P is equal to Q I D divided by volume. It's nothing that is area into thickness, area into thickness, where A be the area of surface of that of dielectric. A is the area of surface of dielectric. D cancel out. So, P is equal to QI divided by A. QI divided by A, charge per unit area, that is the surface charge density. Here the surface charge density due to the bound charge. Therefore, we write charge per unit area will be sigma P. Sigma P, that is surface density of bound charge. So, polarization vector is defined that is equal to numerically to that of surface density of bound charge. Hence, we write that point here. An important point, polarization of a dielectric is numerically equal to surface density of bound charge. Here the charge induced due to that of bound charge, and the unit of P vector, unit of P that is charge per unit area, so coulomb per meter square. Here the unit of P will be coulomb per meter square. In this way, we define the polarization vector P, which is equal to surface density of bound charge. Now, the concept of susceptibility. Susceptibility, we know the polarization of a dielectric is caused by the electric field. As we applied an external electric field when the dielectric slab is placed in between the parallel plate capacitors, so polarization phenomenon takes place. Therefore, polarization should be directly proportional to the net electric field inside the dielectric. As polarization of a dielectric is caused due to that of electric field, so it will be depend upon the net electric field inside that of dielectric. Therefore, polarization vector is directly proportional to net electric field inside that of dielectric. Now, we have to introduce constant. Therefore, polarization vector P is equal to epsilon naught zeta e xi. ja E vector, where epsilon naught, that is the permittivity of free space, or we can say permittivity of air or vacuum, permittivity of air or vacuum, and ja E is the electric susceptibility, electric susceptibility. Look here, in vacuum there is no polarization. If we consider vacuum, means there will be no such dielectric, then there will be no polarization. Hence, susceptibility for vacuum will be 0. Look here, a point to be remembered here. An important point, in vacuum there is no polarization. Polarization takes place due to the presence of dielectric in an external electric field. So, in vacuum no polarization takes place. Since polarization is depend upon that of electric susceptibility, hence susceptibility for vacuum is 0. Hence, susceptibility for vacuum is 0. Susceptibility has no unit. It has no unit. It has no unit in SI system. Why? Susceptibility is equal to polarization divided by epsilon naught into E. Now, the net electric field, we say here the net electric field, here E is equal to E naught minus EP, that is the net electric field inside that of dielectric, is equal to, that is external electric field minus the induced electric field. Inside that of dielectric, EP, or we can say the electric field produced due to the process of polarization. So, the net electric field will be E is equal to E naught minus EP. Therefore, we say the magnitude of that of polarization vector P is equal to epsilon naught ja E or susceptibility ja E is equal to P divided by epsilon naught into E. In this way, we define electric susceptibility. Ja E is equal to P divided by epsilon naught into E. Now, another term which is known as dielectric constant. How we define dielectric constant? Dielectric constant is the ratio of electric field inside the capacitor without dielectric to the electric field inside the capacitor with dielectric, which is known as the dielectric constant, and it is denoted by the letter K. Let us consider two identical parallel plate capacitors with air. Let us consider two identical parallel plate capacitor this is a parallel plate capacitor, another parallel plate capacitor, these two are identical. Let charge on each capacitor is plus q and minus q respectively. Here for plus q, that for minus q, for plus q, that for minus q. Let uniform electric field between the plates of the capacitor is E naught. Here uniform electric field, the strength of uniform electric field be E naught here. Here also the strength of electric field E naught here, that from positive to negative. Now introduce a dielectric slab between the plates of one capacitor, and that dielectric gets polarized, and net electric field inside that of dielectric. Here we take a dielectric slab. Now according to the concept of polarization, that dielectric is polarized, that end negative charge, that end positive charge generated. So electric field is induced here, that electric field direction from positive to negative, that is EP. Therefore the net electric field, here the net electric field inside that of dielectric E is equal to E naught minus EP in that particular parallel plate capacitor, where EP is the electric field produced inside that of dielectric due to induced charges. Now according to our definition of dielectric constant K, dielectric constant K, therefore dielectric constant K is equal to, that is E naught divided by E, as we say the ratio of electric field inside the capacitor without dielectric, that is the electric field inside the capacitor without dielectric, that is E naught, divided by electric field inside the capacitor with dielectric, that is the electric field inside the capacitor with dielectric field E. Therefore K is equal to E naught, in place of E we write that is E naught minus EP, as the external electric field is greater than that of induced electric field EP. Therefore we can say, therefore K is greater than equal to 1, dielectric constant is greater than 1. Here since the electric field between the plates of the capacitor with air or vacuum as medium is given, therefore E naught this is the parallel plate capacitor. So electric field here will be how much? We write here, since electric field between the plates of the capacitor with air or vacuum as medium is given by, so electric field E naught is equal to surface charge density divided by epsilon naught. So here the surface charge density, let sigma divided by epsilon naught sigma, or which is known as sigma f for free charge, that is surface charge density due to the free charge, that is surface charge density due to free charge on plates of capacitor. Again here the electric field due to the induced charge inside that of dielectric, also electric field due to induced charge or we can say that is the bound charge, induced charge, or we can say bound charge inside the dielectric EP is equal to sigma P divided by epsilon naught, where sigma P, that is the polarization charge per unit area of that dielectric slab, or we can say surface charge density due to bound charge, that is surface charge density due to bound charge. Surface charge density, charge per unit area of that of dielectric slab. Now we have to put these values in that particular equation. Putting these values, we have putting these values, we have K is equal to E naught by EP, E naught divided by E naught minus EP. So in place of E naught we write sigma by epsilon naught divided by E naught minus EP, that is sigma by epsilon naught minus sigma P divided by epsilon naught. Therefore taking the LCM, under simplification we have K is equal to sigma divided by sigma minus sigma P. That is the expression for dielectric in terms of surface charge density. Taking that concept, we prefer some special cases, if dielectric sample is metal. For metal, that is sigma p is equal to sigma, then that will be same to that of surface charge density due to free charge. Therefore, K is equal to infinity. That indicates metal has infinite dielectric constant. Metal has infinite dielectric constant. Another special case, if the dielectric is vacuum, if dielectric is vacuum, that indicates sigma p will be 0. Here sigma p is equal to sigma, means surface charge density due to polarization is same as surface charge density due to that of free charge. Therefore, sigma p is equal to 0, so K is equal to 1. It indicates dielectric constant of vacuum is equal to 1. Dielectric constant of vacuum is 1. Next, relation between dielectric constant and susceptibility. How we derive a relation in between dielectric constant and susceptibility. Right, relation between dielectric constant and susceptibility. Dielectric constant and susceptibility. So, here we know E is equal to E naught minus EP. E naught minus EP. Therefore, E is equal to E naught minus, in place of EP we can write sigma p divided by epsilon naught, that is sigma p divided by epsilon naught. Remember a point we discussed in the concept of polarization vector, sigma p is equal to the polarization vector. So, here we replace sigma p as EP, sigma p as P, as sigma p is equal to the polarization vector P. Therefore, E is equal to E naught minus P divided by epsilon naught. Now dividing E on both sides. Here we write dividing E on both sides. E divided by E, E naught divided by E, P divided by epsilon naught into E, that is 1, E naught by E, that is K, as we define K is equal to E naught by E minus P divided by epsilon naught into E, P divided by epsilon naught into E, that is the susceptibility. The susceptibility. So here is the relation. K is equal to 1 plus J, the relation between dielectric constant and susceptibility. This is the relation. This is the relation between dielectric constant and susceptibility. K is equal to 1 plus J. So, with the help of this video lecture, we understand the concept of polarization vector P, susceptibility, dielectric constant, relation between dielectric constant and susceptibility. So, with this useful and informative notes, let me wind up the session. Thank you.